Okay, so this is lesson 611, solids and static liquids. Let's begin by defining pressure. I am sure you have heard pressure repeatedly many times in your life, and I think the context in which you have heard pressure is not far from what it actually means. We have heard pressure on the quarterback, pressure from your classes, or any type of pressure that we use in common day language. It resembles to what it is in physics. So let's define pressure with a sentence. So we can say that pressure is defined as the force divided by the area perpendicular to the force over which the force is applied. That sounds kind of complicated, and we can't summarize all these words into one simple formula. Pressure is equal to force divided by area. And let's remember that this area will be perpendicular to the force, okay? And the units for force are the same ones as we have known since October. That is newtons. Area will have the units meter squared. And one thing to note is that the area can change depending on the shape of the object, okay? For most of this unit, the area will be a circle. I'll explain why. So the units for pressure are units of force divided by units of area, which means we have newtons over meter squared. And there's another way to call this, or to name the units for pressure, these units. We have many units, but the one we'll use right now is Newton over meter squared, or Pascal. So you can say the pressure is 1,000 newtons per meter squared, or 1,000 pascals. Okay, now I want you to consider this question. Would you be able to lie down on one nail? Well, that's very dangerous. Don't try it. How about hundreds of nails? Well, let's look at the formula for pressure and let's see what would happen. And in the meantime, here's a video of me laying down on a bit of nails, which was built by one of my students. Shout out to Jiggy. When I'm sitting down on the bed of nails, well, let's go for one nail, only one. Well, the force applied perpendicular to the nail would be my weight, my whole weight. And the area is so small that the pressure goes up very drastically. And that's because area and pressure have an inverse proportionality. When one goes up, the other one goes down. So when I'm laying down on the bed of nails, and he used, I think, close to 80 or 100, the area increases, so that means the pressure I feel decreases. That's why I was able to lay down on the bed of nails and to have a 10-pound medicine ball on me, and it didn't hurt. It didn't hurt. So now let's write down this proportionality so we don't forget about it. In this case, because the force was constant, because my weight is constant here on Earth, that's why changing the area changed the pressure dramatically. And also the force and pressure are directly proportional. Okay, now let's define density. Okay, let's define density. And maybe you've heard the term density, specific density. And this will tell us how things float, if they float. But for now, we can define density simply as mass per unit volume. And the formula is very, very simple. We're going to use the Greek letter rho. Google it so you see how it actually looks. And that's going to be mass divided by volume. This is why I've been doing a very weird lowercase v for velocity, because now we have this capital B for volume. Let me make it even bigger so that it is obvious it's a different one. And a way you can think about this is how much stuff, how much mass you have in a certain volume, okay? Higher density can mean more stuff in a very small volume, or you can have it's just like that, right? Stuff over volume. So that's why things such as neutron stars have a very high density, because they have a very high mass concentrated in a very small volume. Well, small in terms of astronomical measurements. And rho is density. We'll get to the units right now. M is mass, and we know mass is in kilograms. And in this case, volume is going to be meters cubed. And just like with the with pressure, volume can change depending on the shape of the object. Most of our work is going to be with pipes, containers, and cylinder is going to be the big one over here. So that means to find the units of density, we'll divide units of mass over units of volume. And I put a square instead of a cube. So that means density will be in kilograms per meter cube. And a good quantity to have is the density of water, because we'll use a lot of containers with water. And that density is 1,000 kilograms per meter cubed. And this quantity is very interesting. You'll see as we proceed with the unit. Okay, now that we have pressure and density, I want you to think of times where you have gone to the pool, swimming pool, and then you're trying to swim, and then you go deep, like to the deeper side. Maybe you felt that your ears pop, or you feel just a lot of pressure. And that's because pressure changes with depth, okay? And to show that, I want you to look at this container with fluid, okay? And let's go back to the formula for pressure. We have pressure is equal to force divided by area. All right, let's think about the pressure here for the water, the liquid, this fluid in the container. But what's the force being applied? Well, the force being applied is going to be the weight of the water, the mass of the water, times the acceleration of gravity. Just call that mg. And then, well, this force is being applied perpendicular to the bottom of this container, okay? So if you think of the bottom of that container, what shape do we have? And this is called a cross-sectional area. Let me explain what it is. So if you had, let's say this was a cylinder, right? And if I cut it in half, and then the cross-sectional area is a circle, okay? Just like with this container, the cross-sectional area is going to be a circle. That's how we can find the area. Notice that it's perpendicular, right? That's the radius. So that means we can say, all right, the pressure by this fluid on the container is the weight of the fluid divided by the area. All right, so far so good. Because we have a fluid, we can work with its density. And we know that density is mass divided by volume. So what I'll do is I'm going to solve for mass, and then I'm going to plug it in here in my pressure equation. So to do that, I just multiply times volume. Now we know that mass is equal to density multiplied times volume. So I'm going to combine these two equations and get a new one. Pressure is equal to density times volume times acceleration of gravity divided by area. Okay, how can we find the volume of this fluid? Well, the fluid took the shape of the container. The container is a cylinder, can be modeled as a cylinder. So to find the volume of a cylinder, we need to find the area of the base. In this case, a circle, but I don't have the measurement of the radius, so I'm just going to say that I need to find the area of the base and multiply times the height of this liquid. The height of that liquid is simple, right? It's just here, from here to here. That's the height. Let's call it h, height h. And then to find the volume, we can multiply the area times the height. That's going to give us the volume of the fluid. So now I'm going to combine these two, and then I'll have pressure is equal to density times volume, which is area multiplied by height, times acceleration of gravity divided by the area. Notice that the area will cancel, and now we have a second definition of pressure. Pressure is equal to rho, density, times acceleration of gravity. And I know I called it height, and I needed to call it height so that we would find the volume in terms of the volume. However, when you have a fluid like a pool, we don't really think of height, the height of the water. We think of depth. So when you use this formula, the h will be depth of the water. Okay, and in this case, the deeper you go, right, the greater this h value is, the more pressure you'll have. You'll feel there is more pressure. And so today or whenever, if you go to a restaurant and you're given a clear glass with Sprite or some fuzzy drink, notice that the bubbles, when they go upward, they expand a little bit. The bubbles toward the bottom of the glass are smaller because there's more pressure, because you have a higher depth. It's kind of fun, actually. So this h is depth. The deeper you go, the greater the pressure. Also, all these are directly proportional. The greater the density, the greater the pressure, greater the depth, the greater the pressure. And g is just a constant. So let's write down what this is so we don't forget. And here I made I want to make a clarification because I don't think I was clear. This is the depth of the fluid, not of the container. You can have a big container, but if you have a very small volume of water, then the depth of the fluid is not going to be a lot. Therefore, the pressure is not going to be a lot. Okay? And now let's just make sure we get the units of pressure back. Okay, it's going to be kind of fun. We're going to multiply all these units to see what we get. So we ended up with kilogram over meter times second squared. And if we compare this to the units of pressure, newtons over meter squared, this is mass, acceleration, force, right? And this mass will cancel the square, and we end up with kilogram over meter times second squared, which is a Pascal. So everything works out. That's it.